Hi everyone, I'm Adam Bergasser, and in this lecture we're going to be talking about circular motion. We're going to be looking at different ways of quantifying that motion, and then looking at how we can actually calculate the paths of certain types of circular motion and relate those to our other kinematic quantities of velocity and acceleration. Now, circular motion is extremely common in nature at all scales, from the very smallest scale, cellular size, where you can get several molecular rotors, such as the molecular rotor that controls the flagellum on a paramecium cell. You can also, of course, get circular motion in the way that we move. So the motions of dancers, of different athletic sports, all involve some degree of rotation. When we look at the galaxy, or we look at the universe, or we look at stars, there's a lot of circular motion. For example, when galaxies are colliding with each other, we have to take into account not just their linear motion, but also their rotational or circular motion as they orbit around a common center of mass. And then here back on Earth, we have various forms of circular motion in our weather patterns. A great example, of course, are hurricanes or tornadoes, which are cyclonic motions that happen in the atmosphere. Again, that's a case of circular motion that can expand over very wide ranges of scales, and it's something that we have to figure out how to kinematically quantify in order to study. So let's see how we can quantify our kinematic rotational quantities. Rotation, at some level, you can think about having just a length of a line, and a rotation is really how we pivot that line about one endpoint. So here I've got a line of radius r, and starting at one point where it's at point A, and then this is going to be my pivot point, and as I rotate that about some angle, I trace out a path length, which is labeled L here. So the angle delta phi traces how much that line has moved, and L is an actual path length. All of these quantities are related to each other, of course. The path length is called the arc length, and we can quantify that as the radius times this change in angle, delta phi. We can also rewrite this to actually come up with an expression for that angular change, or what we'll call an angular displacement, because we are changing the angle, and it matters which direction we're changing that angle, whether we go counterclockwise or clockwise. So this can be a vector quantity. The ratio of the arc length to the radius gives us that angular displacement. Now, there's something interesting about this expression when you look at the units. Of course, arc length is a length, so it has units of meters. The radius is a unit of length, so it's meters. So when you calculate the units, you realize that the units of angular displacement actually cancel out. This is a dimensionless quantity, and it's one of a few that we'll talk about in this class. But when we actually give a unit for angle, we typically give a unit of radians when we're talking about angular motion, because that's a convenient metric of this unitless quantity of angle change. And keep in mind that radians is just another unit of angle. We have other units including degrees, and there's relations that converge between these two things. So for example, a radian, 2 pi times radians, 2 pi radians, is a full path around a circle, and so that's equivalent of 360 degrees. So the conversion factor between radians and degrees, there's 1 radian for every 57 or so degrees. So these are just different units for angle. When we talk about circular motion, we're mostly talking about angles in these radians units, because they're the natural unit when you take the ratio of different lengths. Now, let's say we make this angular motion over some period of time. Now we can actually quantify not just the displacement or the lengths, but we can also look at the velocities. So we have several quantities that we can describe for these. One is how fast we're rotating in angles. That's called the angular rate, and commonly we describe the Greek letter omega for that angular rate. And it is a rate. A rate is something that's changing with time, and this is the change of the angle with respect to time. Now that's different from the angular speed, where we're actually looking at how much distance or path this object has traveled as it's gone around in its circular motion. So that's just the total distance traveled, which is the arc length, divided by the amount of time. All right? Just like our regular speed definition for straight line motion. Now remember that arc length is related to the radius and the change in angle, so we can actually rewrite the angular speed in terms of those quantities. So that's just r change in angle over change in time, or it's r times our angular rate. Radius times angular rate is our angular velocity. And notice the units of angular velocity is a length per time. That's what distinguishes it from angular rate. Now, those are scalar quantities. They don't necessarily have direction, although you may want to specify the direction being clockwise or counterclockwise. And we'll talk a little bit more about rotational direction when we get to rotation at the end of the course. But we do have an actual angular velocity, which indicates the direction of the motion in that angular direction, and it's just equal to angular speed times an angular direction unit vector, which we're going to call phi dot. And this is one of our polar vectors. And just like velocity along any kind of path, this vector is tangent to the motion. So in the case of a circle, it is pointing tangent to the surface of the circle. That is the direction of our angular unit vector. Right? So angular velocity can be, just like every other velocity, can be described as a magnitude, a unit, and a direction. In this case, the direction is tangent to the circle. Now we can specify one more quantity, and that's the orthogonal direction of velocity, and that's the radial velocity. That's the case if we have actual motion that's going away or toward the center of our circle. So in a constant circle path, or uniform circle path, which I've drawn there, we would have zero radial velocity. But more generally, we might have both radial and angular velocities. And of course, those combined give us our full two-dimensional space of velocity in this particular two-dimensional path. Now we can take our change one more step and look at acceleration. The change in the angular velocity with respect to time is the angular acceleration. And now this is a little confusing because we don't have a angular rate. We use acceleration for both the angle change and also the distance change. So be careful when you're using these terms that you're specific about whether you're talking about changes in angles or changes in distance. So the angular acceleration is the change in the angular rate per time. It can also be the change in the angular velocity with time. And again, since we can relate angular velocity to the quantities of the radius and the angular rate, we can write this down as the radius times the change in the angular rate, which is equal to the radius times the angular acceleration, but in terms of radians per second squared. So these terms are a little bit confusing because we use the same words. But again, keep in mind that you want to be very specific whether you're talking about angles or actual distances. And you can do that by just making sure you check your units. Now the direction of the angular velocity in the sort of unit, distance per time squared sense is again going to be tangent to the motion just because we've broken down this angular velocity into that component. But of course you can also have you can have accelerations that go in the radial direction, so that's a radial acceleration. And these angular and radial accelerations don't necessarily have to go in the same direction of velocity. Just as we saw with ballistic motion, you can have an object moving in one direction, but have an acceleration that's pointing in a completely different direction, because that's describing the change in the velocity. So when we describe angular acceleration and radial acceleration, we are describing accelerations in two different directions, but they don't necessarily have to go along the path of motion. So now let's go a little bit more detail on specific types of motion, and we're going to start with our constant rate circular motion, so going around in a perfect circle at a constant angular rate. This is described here in the animation you see. And you can see that I've labeled this both in terms of the rectangular coordinates of the motion, x and y, and the polar coordinates of the motion, r and phi. And as we'll see, the polar coordinates are actually a little more convenient of a coordinate system to describe this motion and actually generally for circular motion overall. So how do we describe constant circular motion? Well, a perfect circle is one in which the radius is fixed in all directions. So if we write this down in polar coordinates, the time dependence of the radial coordinate is essentially constant. There's no time dependence at all. It's just a constant radius, which we'll call capital R. So that's a very easy expression to write down. And then the angular motion, if we're talking about a constant angular rate, in that case then we can write the angle as a function of time as the initial angle plus this angular rate times time. All right? So this is very similar to our expressions for constant velocity motion. It's just describing angle in the case of the phi term. Now we can convert this over to our rectangular coordinates by just doing a little bit of geometry. If we break down our radial vector, our position vector, you can see that the x component, the way I've defined my phi, the x component is pointing along the adjacent side, and the y component is pointing along the opposite side. And if you remember your mnemonic, SOHCAHTOA, that means that the x component is the radius times the cosine of the angle, and the y component is the radius times the sine of the angle. Now, notice that now, instead of having just a fixed angle, which we've seen in some of our earlier problems, that angle can change with time. So both the x and y coordinates are essentially time dependent, and they're time dependent based on these trigonometric functions. Now, this is going to be true no matter what orientation our position vector is in, because we can just break down the components into x and y, and it's always going to depend on that time dependent angle. And so where x and y point is just going to depend on what that angle is. Now, if we want to compute the velocity of this particular object moving in constant circular motion, that's just taking the time derivatives of our polar coordinates with respect to time. So remember that our position in radial coordinate space is constant, so the derivative of that, or the change in the radius, is 0. So there's no radial velocity in the constant circle case, which is what we would expect. The change in the angle, of course, we take the change, that's going to be the change in angle with respect to time. That just defines our angular rate, omega. So that just gives us back omega in terms of angular rate. And again, if we want to calculate the actual velocity, then we have to multiply that by the radius, right? So r times omega. And again, the direction of this velocity is going to be in the direction of increasing angle and tangent to the path. So you can see here that the velocity vector, which is all in angular velocity, is orthogonal, or at right angles, to our position vector. Now, as we take another step forward, what we'll see is that the velocity, or sorry, the angular speed doesn't change, right? It's still the same length of vector, but what does change is the orientation, right? So if I bring these two vectors back, we can see that there is a change in the velocity direction. There's not a change in the speed, but there is a change in the velocity direction. And recall from our definition of acceleration that any change in velocity, direction or magnitude, is an acceleration. So we do have an acceleration in this point, so we actually compute what this acceleration is. So we can do this very easily graphically. So I've shown our first time step in dashed lines, our second time step in solid lines, and you can see to go from one to the other is a small little vector that points downward, points inward toward the circle. So the change in velocity is in the negative radial coordinate direction, right, pointing inward. And that change in velocity with respect to time is an acceleration which we call the centripetal acceleration, right? That is acceleration that is needed to change this velocity vector's orientation as the object goes around in a circle. Now, how do we compute the magnitude of the centripetal acceleration? Well, we can do, again, just a little bit of geometry. Notice that the change in velocity is just related to change in angle. So we've gone from this angle, so this orientation here to this orientation here. That is a change in angle delta phi. And because the velocity vector is always perpendicular to the radial vector, as the radial vector changes by that angle, the velocity vector changes by exactly the same angle. And if we just do a little bit of trigonometry, you can see that AC is essentially an arc length. It's very close to an arc length compared to these two velocity vectors. And so that's just described by the length of this vector, which is r times omega, the angular speed, times the change in angle. That's the change in velocity. And now we divide by time, we get another factor of omega. So our centripetal acceleration is just r times omega squared. Now, by the way, you could have figured this out from dimensional analysis. Acceleration has to have units of meters per second squared. So you need a radial coordinate in there, which is meters, and then the angular rate, right, the angular change with the angle with respect to time, gives 1 over second, so we need actually 1 over second squared, so that's omega squared. So dimensionally it gives the same thing. Now we can also rewrite this r omega squared in terms of the original angular speed, because r omega is the angular speed. So this is also equal to our angular speed squared divided by the radius. Right. So both of these expressions will be useful as you're computing things like the acceleration that is required to keep an object in a circle. And of course that's going to be related to the force required to keep things moving in circular paths. And notice that it changes very rapidly with that angular rate or that angular speed. It's a squared power. So if you double that, you have to have 4 times the acceleration to keep an object moving in a circle. Now, those of you who've ever played on a playground and experienced circular motion on something like a roundabout, you've probably not felt an acceleration inward toward the roundabout, but actually felt an acceleration outward, pulling you away. This is actually because we as objects in the universe want to move in straight motions unless we're acted on by a force. And what you're feeling is not the force or acceleration pushing you away from the roundabout, but it's actually your own linear motion, your own inertia that wants to carry you in a straight line direction. And you need to have, again, an acceleration to change your path to keep you going on in that circle. So we'll talk a little bit about this when we get to forces, but just keep in mind that the feeling you feel as you fly off a roundabout is not the acceleration caused by this circular motion, but it's actually a lack of acceleration. You want to move into a straight line velocity, and you're being pulled back, and so you sense that you're going in the wrong direction as you're being pulled out of the roundabout. Now, we've just shown an example of constant circular motion, and notice that the velocity and the acceleration are perpendicular to each other, and in that case, you're just changing the orientation of the velocity vector. And this is generally true for any kind of motion. If you ever have a velocity and acceleration vector that are aligned with each other, then that's mostly changing the speed of the object. So if it's pointing in the same direction, the speed will go up. If the acceleration is pointing opposite the velocity, the speed will go down. We've seen this in our one-dimensional motion several times now. But if you have an acceleration vector that's perpendicular to a velocity, that's mostly just changing the direction of velocity, not so much the speed. And so in general, when you have an acceleration vector pointing at an arbitrary angle, you're going to have a component that changes the speed. That's the one that's aligned with the velocity vector, and one that changes the direction. Now, constant circular motion is just one example of circular motion. It's the simplest example. There are, of course, many other forms of circular motion that we can have. For example, if you change the radial coordinate as a function of time, let's say just linearly moving the radius, you have what's described here in this animation, a spiral motion, right? And that's something we see very often in nature, including things like galaxies. If you change the linear motion of an object in addition to this circular motion, you get something known as cycloidal motion. And this, for example, is the motion of a rock that's embedded in a wheel as a wheel rolls down the road. We'll talk a little bit more about that when we look at our problem-solving video. We can also go into a third dimension and look at circular motion plus a motion along the z-axis, or the third axis in our three-dimensional space. That produces helical motion. And again, that's something we see all over in nature. DNA is in a helical shape. Much of the polarization of light that we see from space comes in circular polarization. And that forms a helical sort of shape as it propagates through space. And there's all sorts of even more complicated motion if you're adding circle motion with another level of circular motion. This animation is tracing out something called a deltoid, and it's doing it by having one rotating portion that's also rolling around in another circular motion. So by combining two different circular motions, you can start to get fairly complicated pathways. Here's another one that is showing the motion of an epicycloid, which makes kind of something that looks like flower petals. And so many of these circles on circles or circles on linear motion combinations of motion give rise to a lot of the complex patterns that we see in nature. And so understanding how to break down those motions into both linear and circular and very distinct ways allows us to characterize not just how these motions happen, but also how these patterns arise. So to summarize, we've looked at several new kinematic quantities that are specific for angular or rotational motion. They have their analogs in our straight line kinematic motion, but they just deal with angles as opposed to straight line motion. So we have angular displacement, which is the change in angle, and that's measured in radians, which is our natural unit for angle. It's a dimensionless quantity, and 2 pi radians is 360 degrees. We have arc length, which is just that angle times the radius of which that angle is covered. And that gives us our sort of displacement or distance, a comparable measure as we have in kinematics. And when we look at that with respect to time, those changes with respect to time, we can either get an angular rate, which is the change of angle with respect to time, or the angular speed or velocity, which is the actual change in the position, the physical motion in units of meters per second as an object goes around in a circular path. And those are of course related. The angular speed is simply equal to the radius times the angular rate. And we can also have angular acceleration both in terms of change of angle and change of position in the angular sense. And all these things are much easier written down when we look at these systems in polar coordinates. And then finally, in order to have any kind of circular motion, we have to have a component of acceleration that's pointed radially inward, and that is our centripetal acceleration. And that's just equal to the radius times the angular rate squared. And as I said, circular motions are often more easily written in polar coordinates, so it's useful to get used to using these polar coordinates if you see any kind of circular motion. But you can always convert these back into our rectangular coordinate systems by just a little bit of geometry. And keeping in mind that these are coordinates that are changing with time because the angle itself is changing with time if it's going around in a circle. And we've seen some of the complex motions that can arise when you combine circular motion and linear motion or multiple circular motions. These are all kinds of motions that we see in nature today, and we can analyze them by breaking it down to this framework of circular polar coordinate systems.